Hi, my name is Kai Struble.
And I'm David Pimley.
And we're seniors studying computer engineering at Purdue University. We're part of the Autonomous Motorsports Purdue team. We want to thank you, Velodyne, for lending us one of your VLP-16 sensors. We think the technology is very exciting and have enjoyed getting to know its capabilities. We're excited to show you how we can use it this May at the competition.
I am the lead software architect of the team, and I'll be taking you through a short demo of what we have so far using the Velodyne sensor.
Thank you.
For this demo, we'll be using the Velodyne VLP-16 Lidar sensor connected to our NVIDIA Jetson TX2. To actually see what it will be placing, we have some free chairs right over here, and hopefully the Lidar will be able to pick them up, and then we can show you some path planning and how we'll navigate through these chairs. For this demo, we will be using a version of Ubuntu Linux 16.04, and we'll be showing exactly how that we can do some path planning using the VLP-16 Lidar provided to us. So there's a few things we need to do before we get started. The first of which is kind of create our directories, which I've already done for time's sake. But beyond that, we need to first launch a few files. So I have a few files here, a cart configuration launch file and a move base launch file. The cart configuration launch file kind of configures the size of the cart and the Velodyne sensor, whereas the move base launch file kind of does a lot of the path planning and kind of the SLAM algorithms that will be being run as the Lidar is also being run. So to launch each of these files, we'll just use a simple command, ROS launch, and then the actual name of the file. So when we launch each file, we want to make sure that no errors, no warnings, so it looks like we're good here. And then these processes at the bottom here are kind of what is being run by this file. So mostly just a lot of the Velodyne drivers are being run, and then a point cloud to laser scan, which converts the 3D Lidar data into kind of a slice, which we'll be using later to actually do some path planning. And then lastly is a robot transform to actually transform the incoming Lidar points back to the center of our robot. So the next one we need to launch is the move base file. So this actually does the SLAM algorithm that we need to actually do the path planning. It kind of facilitates our localization and our mapping. So when we launch this one, just want to make sure that we're good. Looks like we're good. Launching RViz, and this will be the basis of our demo. So as you can see here, this red arrow represents kind of our initial pose right now. So which way the Lidar is actually facing. And if you remember from the video we showed earlier, these three obstacles right here represent the three chairs. So you have two chairs right here and then one more chair right here. And if we take a look on the left side here, we have a bunch of different incoming topics or messages being sent to us that we can use to help facilitate path planning. So if we start at the top, we have our 3D Lidar, which is actually the raw input that the Velodyne sensor is giving us. And for this tutorial, normally we'd be looking at everything that the Lidar sensor has given us. However, for this tutorial, we're just going to be looking at the small square or kind of the local planar. And then, as I said, the Velodyne data is also being transferred into a kind of a 2D map or a 2D slice. And that's what these points represent, is kind of the ranges of the Velodyne points that are being given to us. Aside from that, we have our global planner, and this will come in handy in just a few minutes. And then also we have the cart footprint and the cart pose. So currently I have the cart footprint configured as just the Lidar sensor because that's the only thing we have it hooked up to. But as we connect this to our cart, this will turn into more of a rectangular object that will better represent our cart and where the Lidar is being placed on that cart. So if I take that off, no more pose, take this off, no more actual footprint of the robot. So now we are now ready to kind of do just a basic sort of path planning. So if I just place a path like this right here, give it a second. it'll give us kind of a path that we need to take in order to get there. One of the most important things I had to do in order to get to this place, however, was that the initial ROS navigation stack kind of provides for a differential-like drive robot, whereas our cart is more car-like, where we only have kind of a velocity and then a steering angle. So one of the things that we had to do was to replace the local planner and then use something called a TEB local planner, which kind of converts it to Ackerman steering or more car-like steering. And that's why you don't have really jagged curves. You have more of a smooth curve. And if we get rid of the global planner, this is the exact path that we need to take in order to get to this point. So this is what we have solidified and very functional as of right now. What we are currently working on is being able to create Python scripts in order to actually do its own path planning, to kind of find, if we go back to RViz here, the best way to kind of move about a track or to move about a room in order to map it.